Hi, in this video I'm going to explain how the Hopcroft-Karp algorithm works and how to use it. Before we begin, I'm going to explain some important terms. The first thing is, what is a bipartite graph? A bipartite graph is a graph where, put simply, the vertices can be separated out into two separate groups, where none of the members within a group are connected together. In other words, members of a group don't have edges between themselves. Instead, they may only have edges with vertices in the other group. The second term I want to explain is matching. A matching is a set of edges where no two edges share a common vertex. So a matching for a bipartite graph would be a set of edges linking vertices on the left side to vertices on the right hand side. So, what does the Hopcroft-Karp algorithm actually do? Well, it takes in a bipartite graph and produces the largest set of edges where no edges share an endpoint. In other words, it produces the maximum matching for a given bipartite graph. Before we move on to actually seeing the algorithm in action, there's a couple more terms I should explain. Free vertices and augmenting paths. A free vertex is a vertex that isn't involved in any matching. That is, the vertex isn't the endpoint of any edges in a matching. An augmenting path is a path in the bipartite graph that starts and ends on free vertices and alternates between unmatched and matched edges. The Hopcroft-Karp algorithm is as follows. First, you initialize the maximal matching M as empty, and while there exists an augmenting path P, you remove the matching edges of P from M and add not matching edges of P to M. Finally, you return M. The implication here is that we need to find an augmenting path with each iteration of the while loop. And once we can't find an augmenting path, we have found the maximum matching. A group of friends, Alex, Ben, Charlie, Daisy and Ellie, go to a hat shop, and they all find hats that they want to buy. Unfortunately, the hat shop only has 5 hats. Also, not everyone has decided which hat they want, and are interested in several. The bipartite graph shows which hats each person is interested in. Hopcroft-Karp will be used to get the maximum cardinality matching of the graph, and will match as many people to hats as possible. Initially, all the vertices in the graph are free vertices, with no initial matching. We use breadth-first search to create alternating level graphs, a structure we can use to find the augmenting path. Each alternating level graph is rooted at a free vertex, and when a completed level for a graph contains a free vertex, we stop exploring for that graph. Since this is the first iteration, we have to create an alternating level graph for all the people on the left-hand side of our graph. These graphs will only contain the root and the first level, since all the nodes are free vertices. Alright, so Alex wants hat 1, the top hat, and hat 4, the bearskin hat. Ben wants hats 3, 4 and 5. Charlie wants hat 4 and hat 5. Daisy wants hat 2, the baseball cap, and hat 3, the beanie. Ellie only wants hat 1, the top hat. For this example, we decided to take the first available vertex pair from each tree, if any, but you can actually pick any vertex pair. For each of these alternating level graphs, we find a path from a free vertex at the leaf and work our way back to the root. We then cut off the non-path nodes and remove the nodes included in our new path from the other alternating level graphs. So for Alex, we can pick the path from hat 1 to the root. We then remove the non-path nodes and remove the members of this path from the other alternating level graphs. So we remove hat 1 from the alternating level graph rooted at Ellie. For Ben, we can pick the path from hat 3 to the root, remove the non-path nodes, and remove the members of this path from the other alternating level graphs. We then do the same for Charlie, and again for Daisy. We would do the same again for Ellie, but unfortunately, there are no children that we can create a path from. From the paths we found, we can create augmenting paths by flipping all the matched edges to unmatched edges, and vice versa by flipping all the unmatched edges to matched edges. We can then update our matching set with these augmented paths. This will increase the size of our matching. Now we're on to the second iteration of the loop in the Hopcroft-Karp algorithm. This time, we have only 2 free vertices, Ellie and hat 5, the crocodile hunter hat. So let's use BFS starting from Ellie to create our alternating level graph until we reach a level with a free vertex. So from E, we go to hat 1, to Alex, to hat 4, to Charlie. Charlie, hat 5. Hat 5 is a free vertex, and this level is complete, so we stop here. Now we'll pick a path from hat 5 back up to our root. Okay, note how the path alternates from unmatched edges to matched edges. We convert this to an augmenting path and update the matching with this path. When we do this, there are no more free vertices, and therefore we can't find another augmenting path. So we exit the while loop, and we have found the maximum matching. The time complexity of this algorithm is O e root v. Why? Well, in the while loop, we use BFS when creating the alternating level graph, and DFS when finding the augmenting path. This is a big O of e time complexity. The while loop itself is executed a maximum of 2 times root v times. This is due to the following lemmas. Lemma 1. Let m star be a maximum matching, and let m be any matching in G. If the length of a shortest augmenting path with respect to m is k, then m star minus m is less than or equal to v divided by k. Lemma 2. In each iteration of the algorithm, the length of the shortest augmenting path increases by 1. Therefore, after root v iterations, the length will be at least root v. At most, there are root v augmenting paths left, so the loop will execute an additional root v times more. This yields a running time of big O of e root v.